Welcome to this video. My name's Phil and I am a senior lecturer in astrophysics at the University of Lincoln, and in this video I wanted to have a look at a fairly recently discovered system that has 6 planets in that are all in a resonance chain. We're going to have a look at what that means, but first let's have a look at the actual planets themselves. Well, all of them are classified as sub-Neptunian. That means they are in between the size of Neptune and Earth, so they're in that sort of range there, and they're called sub-Neptunian because they're basically smaller than Neptune, so they're all in that sort of range there. Now, if we go to the first 2 planets, now you'll notice that these planets are labelled as planet B and C. It starts with a lowercase b because actually uppercase, or normally the star itself is actually the primary, so it will be classified as A, and that will be like an uppercase A, but then we always start with B, and it will then work its way out in the higher letters basically as we go out. So planet B orbits 3 times for every 2 orbits of planet C. Now that will be known as a 3-to-2 mean motion resonance. The reason why planet B orbits more times than planet C is because it's closer to the star. As you get further away from the star, the orbital velocity gets less. There's obviously more orbit to go round, so the orbital period is longer essentially. So 2 orbits for the outer planet, 3 orbits for the inner planet there, and that means they always pass each other at the same locations basically, and it's called a resonance. Then the next system, basically the planet C and planet D, the next 2 planets there, same sort of resonance there. You've got a 3-to-2 mean motion resonance there. So planet C will go around 3 times for every 2 orbits of planet D. If we go out to planet D and E, we actually have the same resonance again. So we've got a 3-to-2 mean motion resonance there. So planet D will go around 3 times for every 2 orbits of planet E. And when we get to planet E and planet F, then it changes. This time round, planet E, the more inner one, will go around 4 times for every 3 orbits of planet F. So that the inner ones are a 3-to-2, and then the outer ones are a 4-to-3, so slightly different. And then the other ones, the last 2, again, it's going to be a 4-to-3, so planet F now orbits 4 times for every 3 orbits of planet G. And that's known as like a resonance chain. It's somewhat unusual to have such a large number of planets like that where they're all in a resonance chain as you go further out. Now, how actually were these detected? Well, they were detected with the transit method. So that means that as a planet passes in front of the star, as we look at it, so in line of sight, it goes in front of the star, it will block out some of the light. We can detect that by measuring how bright the star is. The flux from the star, it actually decreases, and we get this U-shaped dip in the brightness, and that will happen for all 6 planets around the star. And if we have a look at the actual transits for all of those planets, then we can see them here. So all the way from planet B to planet G. Now, depending on how big the planet is and its orbit, that dip in brightness will change. So a bigger planet that's got a physical larger size, larger radius, will block out more light. So that should be fairly obvious. That means the star will get dimmer. So the actual depth of that transit will be larger. And a planet that is further away from the star will be orbiting slower. That means that the transit takes longer, because it takes a lot longer to go in front of the star as we watch it. So you'll notice that planet B has a much narrower transit to planet G. So planet B is the one closest to the star, planet G is the one furthest away. So you can see that planet G takes a lot longer because it's wider basically. That's how they were detected. But you can also get more information by using the Doppler effect. So you can get the radius of the planet by how much light it blocks out, but to get the mass, you need to know the Doppler wobble of the star, basically, because a larger planet has more gravitational force acting on the star, so it actually makes it wobble more. So if you have a single planet and star, they will orbit a common centre of mass. Now, because the star is so much more massive than the planet, it will just do a little orbit, and it will appear to wobble. We can't measure the light or the velocity from the planet most of the time, so we can only measure the star. But we can get a lot of information from the star only by how that star wobbles about. Now we look at the light from the star, and if it travels towards us, it will be blue shifted. The star becomes slightly bluer because the wavelength is kind of shortened, it gets compressed a bit in our line of sight. If it's travelling away from us, the wavelength is very slightly stretched and it becomes slightly redder. And we can measure the change essentially in the colour of that star as a cycle, and we can then get the velocity from that, from the Doppler effect basically. Now for a single planet, it would make almost a sine wave if it was a circular orbit, but you've got 6 planets there with all different orbital periods, so the star doesn't do a nice even wobble. It's a bit more chaotic because you've got 6 different planets all pulling on it at different frequencies, so you can see it looks a little bit more chaotic. But that is the radial velocity of the star versus time. So the time is on the x-axis and the radial velocity is on the y. But if you know what the orbital periods of the planets are, you can isolate them out. So when you isolate them out, this is what they would look like. So you've got planet B and planet C there. Now, most of the time, if you've got a much larger or more massive planet, it will create a larger radial velocity on the star. So the star will actually have a slightly wider or bigger orbit if the planet is more massive. Smaller planets won't really affect the star that much. So looking at this here, you can probably make some assumption that planet C is less massive than planet B. Same is true actually for planet D and planet E. Planet E actually is almost flat in comparison to D. So planet D here is having more of an effect on the wobble of that star than planet E. And then planet F and G, same sort of idea really here. You can get that nice wave-like shape from the actual orbit of the star as it moves away from us and towards us. And again, the planets are not the same size, they're not the same distance from the star, so that does have an effect on the actual velocity of the star as they basically orbit the same common centre of mass. So resonance chains generally, they're not uncommon. Our solar system used to have one and it got broken at some point, so don't really have it now. But it does occur quite commonly during the formation process of planets in these disks. So this is a disk around a protostar where the planets actually will form. And again, they're fairly common, but they don't necessarily last for long periods of time. Now, things can break them. So chaotic events like planets getting too close to one another, they actually, because they interact with each other gravitationally, they can alter each other's orbits. You can get close passages by them. You can get external disturbances for its movement in the galaxy, other stars moving past, and that can then break the resonance chain. So they won't last forever. They're not a very long period, or thing that happens for a very long period of time, basically. And once that does occur, then the planet's orbit can become more elliptical. It gets scattered, and if that happens to multiple planets, then they can cross each other's paths and they can actually scatter or eject other planets out of the system. So then you end up with planets out in space without a star. And again, that's very, very common, and James Webb has actually just found quite a lot of them in a nebula just floating around on their own, and some of those are likely to have occurred because they were thrown out of their planetary systems during the formation process. And one of the most common reasons for maybe disturbing systems is stars moving close to each other, so a stellar flyby. And in a galaxy like the Milky Way, or any disk-like galaxy like that spiral galaxy, the stars are orbiting in a common direction, really. But the stars can move close to each other in a way, and that causes a gravitational disturbance on any planetary system that they have. And that can then break those resonance chains. So what does that actually tell us about this system? Because you've got 6 planets there, they're still in this fairly large resonance chain. Well, it tells us that it's probably been fairly calm. It hasn't had those external disturbances, things to break those resonance chains, because it's billions of years old, and in normal circumstances we wouldn't expect to see that in this system. It's something that would only really happen quite early on, and over time other interactions with other stars, the galaxy, internal mechanisms would actually break that resonance chain, and you might end up with planets getting thrown out. So it tells us that maybe this system's been actually quite calm for such a long period of time, which in itself is actually quite unusual for planetary systems. So thank you for watching, and if you enjoy then do check out some of the videos.